Now we're going to talk about the history of computers, and we'll see that this history goes back a long time. So the first precursors of computers were actually mechanical calculators. So machines that had little power above your high school calculator, but they were made with mechanical means. So the first example is obviously the abacus, which comes from China and is at least 2,000 years um, before Christ. So at least. So how does an abacus work? Well, you have a lot of different rods on which different beads are placed. So you have beads here, and the beads can be in different positions. So let's say we identify two positions, top and bottom. And the number of beads at the bottom, let's say, is used to identify a specific integer. Sometimes people also use beads in the middle, so in the center. But the important thing is that a certain fixed limited number of different positions is recognized and is used to encode numbers. So this is what's called a digital calculator. Digital because there is a limited set of positions that can be used, and the beads are not used continuously on this rod. The next item, historical artifact of importance for the history of computers, is maybe the Antikythera mechanism. So this dates back from the 1st century before Christ, and it comes from Crete in Greece. So what is it? Well, it was found at the bottom of the sea, so it wasn't found in a good condition, but it consists of gears, so really wheels with teeth that can turn and lock with each other and can be used to compute astronomical information. So the use is really in astronomy. And it's because of the wheels and because of their positioning, which can vary continuously around the axis, it's not a digital calculator, it's an analog calculator. So the two, digital and analog, are really in opposition with each other. So this is really an amazing mechanism because it dates back from the 1st century before Christ, and it has essentially the same complexity as a clock. Now, picture the Greeks with a clock. That's quite surprising, but that's what they had already. The next item is the Pascaline. The Pascaline, invented by Blaise Pascal, the mathematician and philosopher, and this artifact dates back from the 17th century. So it consists also of gears that you can see here, and some drums with numbers that are there. So by turning the wheels and the wheels interacted and having some clock-like mechanism, Pascal managed to make this machine perform basic tasks like addition, subtraction, and multiplication and division. So a certain limited number of tasks that are of interest in arithmetic operation. Now the next item it was invented by Charles Babbage in the beginning of the 19th century, around there, and it's called the analytical engine. So it's quite similar actually to the Pascaline in appearance, but there's a huge leap in inventing this object. So what is it? Well, it's kind of a souped-up version of the Pascaline. Why? The Pascaline manages to perform a certain limited number of tasks, as I said, maybe 4, a bit more, by encoding those tasks using gears and their interaction. Now, what Babbage realized is that he could also make this whole setup of gears dependent on some other setup of gears. So he could have what he called an engine that he could almost program, to behave like the Pascaline or like some other object. So it didn't have just a limited set of purposes like adding, subtracting, multiplying, or dividing. It could be much more general, and you could start implementing much more complicated operations. So instead of being single purpose or limited number of purpose like the Pascaline, it became really multi-purpose and programmable here. So programmable means that you have to write programs for this machine. You have to decide on specific setups that will help you produce different, solve different tasks. Okay, so who says programs? Says programming, and the first programmer was Ada Lovelace, who started using the concepts that Babbage invented to write the very first program in human history. Now, she didn't really use the machine because the machine was never built. Babbage was so ahead of his time that no one understood the interest and the usefulness of those machines. So even though it would have been possible within the tolerance, the mechanical tolerances of the time to build it, it was never built. Humanity had to wait a very long time before building anything like Babbage envisioned, actually almost 100 years. Indeed, the big developments in computing came with a big event in human history, World War II. There were two main motivations for these developments. The first one had to do with secret communications of the Germans using the Enigma machines. What's an Enigma machine? Well, it's very similar to a typewriter. There are keys here, just like on a typewriter, and there is paper. So you don't see it here, but you can have a strip of paper that gets printed on. Now, on a regular typewriter, I press a certain key, a key A, and I expect the letter A to be printed on the paper, and so on. On an Enigma machine, it's a bit different. I press a certain key, something happens in the machine, and a certain letter is pressed. I can then send, and I can type many letters, and I can type many keys, and many letters will be printed on the paper. Then someone else can use this paper, use the appropriate machine, and retype the encrypted message on his keys, and this time what gets printed is the original message. So you can use an Enigma machine to encrypt and to decrypt. Now what happens in the machine? Well, what happens depends on wheels. So the wheels here are here. There are 5 different wheels on this machine. And the settings of the wheels determine what happens when you press a certain key. And each time you press a key, the settings on the wheels will change. Okay, so the set of wheels is here. So the person you're communicating with should know what settings you used so they can use the same setting and they can do basically the inverse process. Now, the way the Germans did this is they agreed beforehand on a set of settings for every day that they would use. Now, the British knew, basically, the British and the Polish actually, so the British at Bletchley Park a little bit after the Polish who broke it first, they knew basically that much. They knew that this was the general setup that the Germans were using, but they didn't know the settings that were used actually in the wheels. What they did know, however, is that the Germans were communicating certain information consistently. So every day, some guy on his submarine would send some kind of weather report so people in Europe would know what weather was coming. Things like this. So they knew that they should be looking for certain words, greetings also. So what you could do is you could take the encrypted message that could be overheard over the radio, and you could try a setting and see if that setting contained a word that you would expect to be in the message. And if that didn't work, if the decryption using that setting would contain the word you expect there to be. And if that didn't work, well, you should just go to the next setting and try again. Of course, there are many, many, many settings that could be possible for those wheels. There were 5 wheels with dozens of different positions. So you had to find a way to do this. And Alan Turing, who was here, found a way to do that. He constructed a machine called the bomb that basically was running through all the different settings and tried to find which setting was explaining the message. So the bomb is interesting because it used punch cards as input. Already Babbage's machine used punch cards. So a punch card is just a cardboard card with holes in them. So here you see the holes. And the holes are, again, digital information because the holes can be there or not in very specific positions. So there's a finite set of positions that can be, finite set of punch cards that are relevant. And they were used to encode the information, the input for the machine. Later on, that machine was perfected into the Colossus that could perform more tasks than just the bomb and was more general purpose. Now, the second motivation for war work had to do with the atomic bomb. So in the Manhattan Project, which took place at Los Alamos in the desert in the US. So working on the Alamos project was Richard Feynman and Metropolis, and many other scientists. So Richard Feynman is probably one of the most well-known of those people, future Nobel Prize winner in physics, very interesting character, wrote a lot of books, and among them his biography, Surely You're Joking, Mr. Feynman, a very good read. So anyway, Feynman and Metropolis had a lot of computations to do with simulating what would happen when a bomb exploded. Okay, so they were employing people, mostly women actually, to do those computations. So they had calculators and like you would have in high school, and they were performing all those computations again and again and again. Now they started talking to von Neumann. Von Neumann had invented on the East Coast a machine that was essentially a very advanced calculator, and you could start programming. And of course, the usage for such an important project led to new development in von Neumann's machine and evolutions in that machine. So in those 5 years of the war, and maybe a few years afterwards, a very important transition happened in the concept of calculators, because we went from calculators that could perform very specific tasks in very elementary ways all the way to computers. So this can be related to 3 different transitions that had to happen. The first is to go from analog to digital, so we saw the punch cards. The other one was to go from mostly mechanical, maybe electromechanical devices to electronic devices. And the third evolution, the most important one probably, is to go from a single-purpose computer, a single-purpose calculator, a calculator with very limited set of tasks that they can perform, all the way to a programmable computer. So what happened? Why was this possible in this big evolution was possible in those 5 years when no big evolution happened for the 100 years after Babbage's invention? Well, of course, the war was a huge motivation, but also so many people were working on this that at the time, there was just so much manpower available, actually woman power available during the war, that they were able to bridge the gaps in the technology. Meaning you didn't have to construct a machine that would move around the punch cards, because you could just take humans to do it, and you could just tell them, take the input or the output from this machine, this punch card, and bring it to this other machine. So the humans were performing some part of these tasks that were later replaced by electronic means. So Feynman, in his biography, I think, has a very interesting passage where he relates this moment where progressively the humans were replaced by the machine, and for a while the two were competing. So all those people with calculators versus the big computer that is sitting in a room consuming a lot of energy. And for a while, the humans were winning, but of course, this is not true anymore. Nowadays, a computer can perform way more computation than any human can ever perform in his life. So with the end of World War II came new developments with the hardware. But those developments were very incremental, meaning they didn't bring any fundamentally new functionalities, they just improved on the previous one. So to improve on speed, for instance, and reliability, the vacuum tubes in the old computers that were prone to break were replaced by transistors and semiconductors. For facility of use, the punch cards that were used for input were replaced by keyboards and things like that, so you don't use punch cards anymore. And for persistency, so to be able to keep the data for a long time and to keep a much larger amount of data, the punch cards were replaced for persistent storage by magnetic tapes, or nowadays by hard disks, or maybe magnetic tapes if you really have a lot of data. So if you compare a computer from nowadays and a computer from around 1950, they can basically perform the same type of task. The main difference is on the scale. So the scale of the speed, the scale of the storage, all those things are very different now than they were in the 50s. For instance, there is something known as Moore's Law, which is an informal law that says that the growth in computing power of computers is exponential. So every 18 months, the computing power doubles. So the computer is capable of performing twice as many operations in the same time. So far, there haven't been massive changes in what a computer can do. Just its efficiency has changed. I say so far because some people think a new type of computers called quantum computers will be able to change that and will bring fundamentally new capacities. But those are still prototypes and they're still not used widely or expected to be used widely in the next 10 years, let's say. Now, one area where there was a lot of change was the software. So the software is, if you want, the next layer, and it helps leverage the capacities that are present in the hardware and helps it leverage more easily and efficiently. Now, if you think of the internet, for instance, of course, the backbone network has to exist, but the internet is really an evolution of software, new possibilities brought because computers can start talking to each other. We're still figuring the part of the software, meaning that there is no optimal solution or no really optimal solution to do different types of tasks. So for instance, there is a wide variety of programming languages and a wide diversity of operating systems. So in this course, we'll see one programming language, Python. But before we can do that, we need to talk a little bit about the components of a computer so we can understand better what we're trying to do with a programming language.